Okay, so this is sort of the last lecture before the final exam review, but there's nothing too new that I'm going to kind of introduce during this lecture. So it's primarily just meant to be a wrap up and to make sure we've covered all the VRT topics, because that's kind of the last kind of thing you're really responsible for the final exam. So looking forward, we've got today's lecture. This week, of course, no labs, but there's, you can, the time during this week is sort of meant to help you, develop your project or to get answers or feedback on your project. Thanksgiving break is this week. Course evaluations are available. So you can, I think those will be open until December 1st, the night of December 1st. After Thanksgiving, that Tuesday, a week from today, will be the final exam review. So there is an ICA that's due before that lecture. There's this ICA MA practice is basically the midterm ICA review that you have access to as a practice. And then this final exam review, after the lecture starts, turns into a practice exam. You can take it as many times as you'd like afterwards, just without any credit. But before Tuesday's lecture, you can take ICAM as many times as you would like, and it'll take the highest score. So it's a good way to sort of buffer your ICA scores if you want to bring them up here. There are practice exams available, practice problems, and so on. They're all in the midterm module. You'll have to take that lockdown browser compliance test in order to the final exam version, in order to open up that module, but then you'll get access to those resources. So I know some people have already done that because I've gotten some questions on the practice exams, and that's fine. If any questions come up about the practice exams, feel free to send me a note, and we can sort of review those things. Then that last week class on Wednesday night, that's when you have to upload your presentations, a 10-minute video upload to Canvas, as well as your project report at the format that has been specified. The main content is 4 pages of content, excluding title page. You need to include any more info, you can put it in this appendix, but you should imagine that the grading is kind of going to be done based on the main content. And so there should be enough information about your model to sort of make your argument within the 4 pages of the main content. And then you should say, like, you might show me the basic parts of your model in the report, but then you can then reference, the full model is given in the appendix in figure, A1 or something like that. So everything in your appendix should be referenced so that your appendix isn't just supposed to be a grab bag of information that the reader has to parse. You should still reference it in the main document, but the content in the main document should be enough to make your argument. Then by Saturday, all you'll have to do is the peer review. So after everybody's, everybody get things in by 11:59, Canvas will randomly assign everyone individually another presentation and another report to watch and to read before Saturday, so that Saturday night you can submit a peer review. And that you'll make sure that you click the view rubric when you do that peer review, and you fill out the numerical rubric, as well as add a comment that's constructive. And I'll be looking for both your scores and constructive comments. And if I see both of those, then I'll give you your check for your peer review of the presentation and the report. Keep in mind, as you're doing these Canvas will assign you a presentation report, and they may not be from the same group. So don't look for agreement there. There are several groups that might be doing the same system, and you might just randomly get the same system, but it might be a different group. So just keep that in mind, that's why they may not fit together. And then the final exam. So then Thursday of the last week of class, we'll have the stage 1. It's similar to the midterm, kind of an extended availability window, but you're given 90 minutes to do stage 1. So once you start it, the clock goes, and then you've got 90 minutes to finish it. And then stage 2 will be collaborative during finals week. If you would like to come here on that Thursday of finals week to work on the stage 2 with others, that's fine, but you don't have to. And again, it's got an availability window that's on Canvas where you've got plenty of time to work within that availability window. It's not timed. So it's exactly the same format as the midterm. All right, so with that, any questions? Yeah. Yeah, it's cumulative, but I would say that, I mean, we haven't really done a whole lot after the midterm. We've built on things that we started before the midterm. And so, like, I might ask you to do a chi-squared test, just like I did in the midterm, but it will be a chi-squared test of an arbitrary distribution instead of a uniform distribution. And so I'll probably blend those things in. Some of the basic concept stuff, like definitely know how to do a hand simulation. Definitely be able to read a hand simulation table, know what an entity is, know what a resource is, those sorts of things. So the kind of vocab and kind of lower level, you know, things in Bloom's taxonomy you'll get from before the midterm. I want to make sure those are kind of held on. But the more higher level things will probably be merged with things after the midterm, because it is only a midterm length exam. So I don't really have the time to or the space to do like a separate midterm and a separate final. And so I'm going to try to sort of assess your midterm knowledge using questions that also blend it with your kind of post-midterm knowledge. So other questions, and I'll look online too. Okay. All right. So let's do an attendance exercise just to, this will kick things off here. So the link is on the slide. I'll see, since this is PowerPoint, I think it'll actually let me type. So you can see the question on the slide. What is the ultimate goal of variance reduction techniques in simulation studies? In other words, why do we bother with VRT? Of course, it's to reduce variance, it's in the name, but ultimately, like, to what end? Why are we reducing variance? So what's the goal there? So that's our attendance question. Okay. Just leave that up for a second. Link there, question down there. All right, so what I hope you put down is that it's to use fewer replications. So simulations, although in theory, simulations can run faster than real time, they still can take a long time. And so if you need to run hundreds of replications, then that may, and then you need to change something, or maybe you discover that your simulation was wrong, or there was a bug, something like that, then you have to run those 100 again. And so it can take a long time and a lot of computational power, and which might mean, you know, actual dollars you have to spend on a high performance computer renting out time, or on the cloud in AWS or something like that. So we'd like to do it in as few replications as possible. And so that's what VRT does. If we design our simulation in a clever way, maybe we can use fewer replications and be able to make the same inferences. So we do that by controlling, which is a fancy name for accounting for sources of extra variance. So we either design our experiment so those variance sources get flushed out before we take the measurement, or we take additional measurements that help us account for variance so we can kind of subtract them off. And that kind of summarizes these 4 VRTs that we talked about in the last unit here. So CRNs, AVs, importance sampling, and I'm going to do a quick review of these just so we're all on board, as well as control variates. I separated out control variates because this control variate idea can really be used in any experiment, not a simulation experiment. It could be used anytime you do any sort of real world or sim setup. You can use control variates to try to account for variance that you can measure and predict from other sources. But these 3 are kind of something special that we can implement in simulation, primarily because we control the sources of randomness. And so we can toy with those random, we can make sure the randomness is duplicated in particular ways, or we can increase randomness in some areas and push it down in other areas. And those are things that we get because we're doing simulation studies. And so we can't exactly move these into real world systems, but we still have to use the same statistical thinking that we would apply to any real world design. when we're doing these. And so this is a quick review of those. If we look at like CRNs, graphically, how would I summarize what's going on in a CRN? Remember, CRNs are for relative estimation. I'm trying to estimate the difference between one model and another. Are these two models performing in a significantly different way? And so I've got one sim model here, another sim model there. I run a replication of both, but into the replication of both, I use the same random number seed. And so that's going to generate the same set of random numbers into both sims, which may end up generating the same, say, customers in both sims. So then I run each sim for like a day or whatever my replication length is. It generates a metric for that day, like the average wait time for customers. And that does that for the other one as well. So on this day with this random number seed, in other words, these customers, I have this performance output from this model, this performance output from this model. They are dependent in that they both are kind of related to the same customer stream. So I subtract them, and that difference ends up actually being the output from replication one. So I run both sims and generate a difference, and the difference is actually the output that I'm going to study. I do that again for another replication. So I put in another random number seed, generate, say, another set of customers into both models. I generate an output from both models, take the difference. That difference is what I get for replication two. And I do that over and over again. And I can generate sort of a table here, and each row represents a new random number seed. And so for every seed, I get a different difference. And so I'll get a whole bunch of differences, one for every replication, and I could generate a confidence interval on those differences and ask, is 0 included in that confidence interval? If it is not, then I can conclude one of the models is significantly different from another. If it is included in that confidence interval, then I can say I either need to generate more replications to get a sensitive enough study to understand the difference between these models, or if the confidence interval is already pretty tight and 0's in the middle of it, I can say, for all intents and purposes, these two models are effectively the same. And that's CRNs. So any questions about CRNs before I move on to AVs? And I'll leave that up. Does that make sense? Questions online? All right. And if I don't want to use the confidence interval approach, I could also just do a t-test of these data and test against the hypothesis that these come from a distribution with a 0 mean. That's the same thing as asking, is 0 in the confidence interval? All right, so then the kind of related idea for absolute performance measurements is antithetic variance. And so here, AVs kind of do a similar game with the random numbers, but I'm doing it to estimate an absolute performance measure from a single model. So I've got one simulation model A, and I'm going to take a random number seed, and that's going to generate a bunch of uniformly distributed random numbers between 0 and 1. That's going to go into simulation A and generate a performance measure. Then I'm going to take each one of those uniformly distributed random numbers, which, remember, every random variate you generate, an exponential, a Weibull, a normal, whatever, behind the scenes, the computer first generated a random number, in other words, a number between 0 and 1, and then converted that into your variate using something like an inverse transform technique. So we always start with random numbers between 0 and 1. So that's how this antithetic variance always works, is it can take all of those random numbers that went into one simulation model, take 1 minus them. So notice 0.25 goes to 0.75, 0.8 goes to 0.2, and so on. And those then go also into the simulation model in a different replication. And I get an output for one set of numbers, an output for the other set of numbers, all corresponding to the same random number seed. And then I take the average, not the difference of those two. And that average becomes my output for replication one. Then I do that again. So I generate another random number seed, which generates a new set of numbers for one replication. And then, or one, I'll call it, pseudo replication. And then I do 1 minus those, and that generates a different set of numbers for the other pseudo replication. And then I take the average of the pseudo replications to give me my actual replication output, my independent replication output. And then that will go into my table for this replication. I do that over and over again And so for this seed, I got this average. For this seed, I got that average. And the confidence interval of this will end up being an estimate of the actual performance measure. So not the difference between two performance measures, the actual performance measure. And I can use that confidence interval to sort of give me an idea of where the real performance of the system is. And if I need to take more replications, then the confidence interval will collapse more around maybe what's closer to a better estimate of the real average. And that's antithetic variance. So that's for absolute, and CRN is for relative. You can think CRN's got an R in, R is for relative, absolute or antithetic variance got an A in it, A is for absolute. So any questions about those and the difference between those? CRNs are for two models, AVs are for one model. They both kind of do a similar thing though. AVs use an average, A for average. CRNs use a difference. Don't have much mnemonic for you there, but yeah. Okay. Questions online about AVs? Okay. So we call them antithetic variates because each average is a variate because the averages themselves are random variables. So that's where that variate comes from. All right. So then importance sampling. This is one where I can beat up on some companies here. So this is, you know, as engineers, we know it's never possible to engineer away all failure. Of course, when we sell products to the general public, they never want their products to fail. We know that products will fail, processes will fail. This whole Six Sigma thing, you know, is this idea that, you know, we are going to have failures, just hopefully there are few enough of them. And if there are actually too few failures, then maybe you can cheapen the process because you can tolerate more failures by your Six Sigma standard. If there are too many failures, maybe you need to work on figuring out where to improve to reduce the failures, but you're never going to reduce the failures to zero. But, you know, as the failures get really small, the failure rates get really small, it becomes difficult to estimate what the actual failure rates are. So, you know, how do we estimate rates of rare failures in these complex systems? And this is very relevant because, you know, so this is an example of Samsung from a couple of years ago. This is a top-loading washer model that they've had, that they had to run a huge recall, extremely costly, because it was rare, but it happened enough that it became a thing that this washer would be going through its spin cycle and the top would pop off and the drum would go flying out of the washer and into, like you can see this hole in the wall here. This injured people, like this thing popped off and hit people who were just trying to do their laundry. And so it was a major problem for Samsung. They had to replace all of these washers with ones that more securely, you know, fit on this top here. And so that was an example where I'm sure Samsung knew about the possibility of this top coming off. I mean, it's made to be able to come off, but they estimated this failure rate to be far lower than it actually was, and that ended up costing them. And so that's kind of the story about that. Samsung recall washing machines affects millions of consumers. And then, you know, on top of that, Samsung's really bad about this. Apparently, if we look at the news, you know, around the same time, different division of Samsung, you know, they had phones that would burst into flames. You couldn't take a Samsung phone on a plane for a while because there was too much risk that your Samsung device would burst into flames while your plane was in the air. So you had to check them at the door. And so that was another example where there are these rare failures with the lithium batteries that Samsung was using that would cause these failures. And so they underestimated this failure rate. And I don't want to beat up just on Samsung, although it's easy to, but there are, there are other examples, from Boeing, for example. So the 737 MAX 8 that we've seen a little bit more recently. And this was an example where they had a control system, which in order to compensate for a change in how lift was generated, there was a control system that would automatically cause the plane to maneuver in a particular way that if the pilot wasn't aware the control system was doing this, they would think that the plane was malfunctioning, and then they would end up trying to compensate. And so you got in systems thinking what we refer to as an escalation behavior, where you had two feedback loops that are trying to regulate different points fighting against each other. And it led to the plane, it would pitch up, pitch down, it would go, and then it would sort of get into this long oscillation until the plane would trend down to the ground, and led to, you know, a couple of crashes and deaths. And that came from not sort of understanding that this event was less sort of, they thought it was going to be rarer than it would. And they also thought that pilots would be trained to respond, to know what was going on here, so they wouldn't get into this kind of escalating feedback loop. Now, what was crazy about this is that they actually, in a flight simulator, they before they even released this plane, they got this failure mode. And the people who used the simulators, the simulation, found this event. And the people who, the sim engineers, the sim pilots that were doing this, flagged it as a major potential problem. But in the sort of chain of custody of that reports, when it hit marketing or something like that, then they end up deeming that it was probably not something that they need to worry about on the production models, when in reality, this was totally predicted using simulation of all things. So, so this was kind of a breakdown, not of our ability to model, but our ability to trust models. So it's, you know, a sort of interesting example of that. So, so this is, you know, a case where, you know, importance sampling can help find these types of cases here. So you have to remind what is importance sampling here? Well, what do we mean by important? Important really is just a name for saying rare events. So they are important because they could potentially be very costly. So we want to estimate the frequency of these catastrophic events, ideally in simulation, not reality, because we don't actually want these catastrophes to happen in order for to measure how frequently they happen. But how do we trust our estimates without getting huge numbers of replication? So if it really does take 1 million flights to get this to happen once, do we have to actually do a simulation of 1 million flights before we actually get it to happen? And so that's where importance sampling comes into play, is that we say, well, all of our stochastic simulations have got inputs, like for a plane, the inputs might be the weather for that day. They might be wind conditions or whatever. Like there could be certain things that are just easier for us to model randomly. And we have a distribution of the normal set of, say, disturbances on a plane that we would expect to see in our simulation. Now, that it might be that the particular case that causes this catastrophic event corresponds to inputs that we very rarely get. So maybe they're in this tiny little tail over here. And so in order for us to really understand the frequency of these things, it seems like we need to run that input model as is and just wait for the inputs to come up here. And then that way we can properly, you know, our denominator will sort of account for the rareness of how often they happen here versus all of the other conditions where they won't happen. But importance sampling gives us a methodology to do a type of stress testing in simulation, where we can kind of load the dice so that we can take our input model that was centered here and shift it over so that we get a lot of those input conditions that generate catastrophic events. And we can then measure how frequently things happen if we lived in this bizarro world where everything was kind of in these really bad conditions. And then importance sampling gives us the ability to translate that back into this world. So if we know, you know, if we know sort of the frequency of our loaded dice, so we kind of know, like, you know, how often things occur in the bizarro world and how often they're supposed to occur in our world, we can take outcomes from the bizarro world and scale them down so that we can actually estimate the frequency of how much they would happen in the real world. And that's what importance sampling is doing. So, you know, the example I have here is we've got a bunch of replications with typical input data. We run them into simulations. They generate performance measures, but those performance measures are all pretty typical. I mean, that's kind of the definition of typical. So they don't generate hardly any of these rare events. So instead we do stress testing where we change the inputs so that they are way out of norm. I mean, we bias the inputs so that these inputs they don't look at anything like reality, but that generates for us a lot more outputs, which are in this important group. So generates a lot of these outputs that have these catastrophic outcomes. And we can measure how frequently they happen when you use this input, these kind of incorrect inputs. And then if we then tabulate all of that, so we have all of our pathological replications, we have the pathological outputs, we flag whether these pathological outputs are interesting enough, so are they catastrophic or whatever. And if we just need to count how frequently they are, then that becomes our output, the frequency, whether it's 1 or 0, interesting or not. So I can scale those by these likelihood ratios, which are just going to be the probability density of that pathological input in the real world divided by the probability density of that pathological input in the bizarro world. And that scaling will change a 1 into something far less than 1, and a 0, well, into 0. And then if I take the average of that frequency will actually be the rare event frequency, as opposed to this inflated rare event frequency I get without the scaling. And that's what goes on in importance sampling. So we're using these data here with the scaling to generate a confidence interval on the real world of how frequently we expect this to occur. So any questions on importance sampling? I'll leave that slide up. Does that make sense? This weird thing where all semester I've been telling you about how important it is to have good input models. You still have to have a good input model because you're going to use that input model at the end of this process. But the weird thing is the simulation is going to use a totally made up input model that just happens to have the same support as your input model. But that made up input model forces the sim to behave badly so that you can measure how often it'll behave badly when you use the good inputs. Okay. All right, so then the last one that I want to make sure that you've got here is control variates, which you actually can use in normal everyday experiments, non-simulation experiments. And so the idea here is I've got, say, 2 simulation models and try to compare their performance. And so there's going to be a difference in performance just due to the fact that they're different models. But there's a common input that might go into each one of these simulation models, like the weather. And so if I can measure that input going into this simulation model, I know that that some of this input that's going into the both, I can use that to account for some of the variance that's coming out here. So if I can't control all of the if I can't, like if this is a factory and this is another factory, if I can't control all of the conditions to make these factories otherwise identical, if I can at least measure the things that are different between them, then I can use those differences to subtract off the variance due to those different conditions so that whatever's left over is actually the different factory process that I'm trying to simulate here. That's what I'm doing in importance sampling. So real world input X that's difficult to control but easy to measure, and then we've got, say, our inter-arrival times that may be easy to control, like CRNs. And so so we're going to compare these outputs, making use of the information we have going into these that might be different here. So let's see that kind of written out here. So the idea here, say for the absolute performance case, which might be a little bit easier to think about, is I've got one model that I'm just trying to figure out its absolute performance. I have these inputs going into the one model. So these are like customers, these, or could be temperatures or whatever. And so the idea here is that I might have a string of customers that are really sort of difficult because, like, let's say it's very bursty traffic, a lot of customers coming at once. Or maybe I've got sort of easy customer traffic down here. And so that easy customer traffic might have a lot more spacing out between them. And so it's not quite as hard on the particular simulation model. And so whatever it is, so let's say these are inter-arrival times that are going into here, I can take an average of this input, and say that's down here. That's supposed to be an X bar, but I think PowerPoint got rid of the bar. It looks like an X dot, but that's supposed to be an X bar. And I can take the average of these interarrival times. Again, that's like an X bar. And so I can take, so right there, I can say, well, this interarrival time average is 2.3. Now, I know from my input model, it should be 5, but I'm just had bad enough luck that it just happens to be 2.3 in this one. This one's 6.15, which again, I know from my input model, the real population average should be 5. So here I can actually measure that this one's customers are much worse than the average. This one's customers are much better than the average. And I can use those differences to sort of account for some of the variance in the output differences here. So, how I do that then is, I'll just get to the point where I do the math here, is that I can subtract off, again, I think I'll just sort of skip ahead here. So if I have my output from each replication, I have the actual, say, average interarrival time from the customers that ran through that replication. I have the known mean population. So I expected the interarrival time to be 5 minutes on average, but for this replication, it was 2.3. Maybe for another replication, it was 6.7. So I can measure the difference from the actual average interarrival time. And I can subtract off whether this was a difficult simulation or an easy simulation from the actual output. And I do that across all of my outputs. And I'll still have variation in my outputs, but some of the variation due to the differences in the customers will end up being dealt with. And I just need to choose what scalar here to kind of best minimize this variance. And so I know a formula for that. So I do a little calculus and I figure out that it's the covariance of my input to my output divided by the variance of my input. So if I plug that into this formula, then I get my control variate formula here. So I've got my measured outputs, I've got my measured inputs, I've got my expected input mean. The differences between that per replication gets scaled by this thing. And then that subtracts off a little bit of the output so that the resulting output has actually got a compressed variance so that it will have a tighter confidence interval. So that's the idea there. And I can just rewrite that in this form here, and it sort of adds a little bit of interpretability. So you can kind of think of this quantity as sort of a kind of a z-score of the X input variate. And this is sort of a conversion from X variance to Y variance, if that helps again with interpretability. And that ends up subtracting off what we need so that we can end up getting a table that looks like this one, where we've got a bunch of replications, we've got our inputs, we've got our normal outputs. We, from those, can calculate the mean of our inputs, we can calculate the variance of our inputs, we can now calculate the covariance of our inputs and outputs together. And then from that, we can then generate the control variate. And notice the control variate is just the output minus this formula, which I used these terms to plug in. And then the variate here has got the 7.5 minus the mean that was calculated here. And that ends up generating my control variate. And those outputs there will end up being used as a surrogate for these outputs. And so the mean of these and the mean of these in theory should be the same, but the variance of the ones in green here, the control variates, will be lower than the variance in these. And consequently, the confidence interval of my normal output is much bigger than the confidence interval of my control variate. So the normal one includes 0. So I actually can't tell if my null hypothesis is that this output's equal to 0. I can't tell whether it is greater than 0 or less than 0. But with the reduced variance, now when I calculate that confidence interval, I see the confidence interval does not include 0. So that tells me that I actually do have a significant result. And so that my performance is significantly greater than 0. Here, I need more replications to tell. Here, with the same amount of replications, I can actually tell the difference. And so I didn't do anything to the experiment. I just measured additional sources of variance and then subtracted off the variance from those measured sources that were separate from the thing I actually cared about. And that improved my estimation of the performance of the system. So that's what control variates are about. Very closely related to general linear modeling or multivariate linear models, where you've got a bunch of different factors and you really only care about one of them, but you still have to account for all the other ones. And this is where accounting for some of those other factors that could be getting in the way. All right, so any questions about control variates? You can do this again with any experiment, not just simulation experiments. Okay. All right, well, that, those VRTs, that was kind of the kind of the last kind of big thing and the new thing in the class that, again, I want to make sure that you've got a handle on, at least knowing the difference of those categories and roughly how they work, especially, say, CRNs and ADs in particular. So with that, let me do another attendance exercise here. So I'll put this back in the chat here, but the question there is there. So which of those 4 VRTs, you just have to name it, generates inputs that are purposely biased to greatly increase the number of normally rare output events? So we're estimating the frequency of rare events. Which one does that? So if I get my mouse back, I'll put that on the chat here. Okay. So as a review, we're talking about either common random numbers, CRNs, antithetic variates, AVs, importance sampling, or control variates. So those are the 4. So one of those 4 is the answer to this. All right. So, so now for the rest of the time here, I just want to kind of review where we've been and where we came and what we use all this stuff for. So just as a reminder, we've been talking about simulation. We have primarily been focusing on discrete event system simulation, but simulation is broader than that. There's also agent-based modeling, which we've seen a little bit in one of the labs, in lab 4, and also system dynamics modeling. And so, if you've ever taken or know people that are in IEE 477, that is a simulation course that's all built around system dynamics modeling. There's also courses in like sustainability. So I teach actually this semester SOS 212, where we do system dynamics modeling in different tools. And it actually follows right alongside very similar concepts in 477. And even in WP Carey, they do system dynamics modeling. So, so simulation is much bigger than the discrete event system simulations we use in this course. There are a ton of different simulation languages, some which are focused on one particular type of sim and some that are multi-model. I think there's at least one group that is, I think, using, actually now I think Visio now connects to, say, Simulate. So you can actually then, behind the scenes, another tool will be running your sim, but the front end might actually be different. So we're even seeing other mashups to generate these types of sims. So there's a lot of these different tools, but the point here is I don't want you to come away from 475 thinking this was an arena class or something like that. I hope you can see that there are fundamental concepts that if you learn one of these sim languages, you can learn the others. You just have to say, all right, where do I generate my entities? Well, as long as you know the term entity, you can look up where to generate entities in Simio and any logic and so on. So there's fundamentals that kind of permeate these things. And of course, you can just go into Python or MATLAB or R and write up your own sims yourself. So again, this is not meant to be an arena class. There's a ton of different sim languages out there, and we just can't cover more than one of them in the scope of a class, or else we'd pretty much just be only doing sim languages in the whole semester. So the general pattern that we get in any language or any sim project that you have is going to be formulating a problem. Hopefully, again, you felt this as you're working through your final projects, formulating a problem, coming up with your objectives. We want to minimize wait time, things like that. On the input modeling report, a lot of you described a system, and I tried to give you feedback to say, okay, it's great if you've described the system and told me that the system frequently has operational issues like long queues at lunch, but what are you going to do about it? What are you testing? Like, and that's really the kind of thing, the objectives. Like, I want to see if adjusting X will affect Y. That's kind of our objective for the simulation. And so once you've done that, you can conceptualize, well, how am I going to build the right model? Like, why is a simulation model the best thing for that? And so how am I going to build a simulation model to capture that? And then as I'm building it, I have to also be collecting data to parameterize it so that I can actually then put that stuff in there. And so I come up with my concept of my model, I'm generating my data, I translate that into code, I test my code in V&V, so the verification step, that's making sure that your code is actually correct. The validation step is checking to see that you've included all of the right structures and all of the right variables to really be a good proxy for the real system. Once you're confident you've got a good surrogate for the real system, you can do a design, an experimental design. So maybe you'll use common random numbers to do a relative performance estimation. Maybe you'll do something else. You do the sim runs, you do the output analysis, you use your stats for that. So hopefully you come out of this class and you're always hesitant to ever just report an average. Please, after you leave this class, if you report an average, at least give a standard error of the mean, plus or minus. Just get used to typing plus or minus whenever you report any performance measure. And if you don't like typing plus or minus, just give brackets in a confidence interval. It's totally fine to omit the mean and just say, I don't know what the real population mean is, but it's somewhere between X and Y. And that will be far more honest and clear about what the simulation gave you. And if it also will tell your stakeholders like, oh, wow, this is a giant confidence interval. How could you possibly move that down? And then you can say, well, pay me more, and I can then pay for additional sims to bring that thing down. If you just report the mean, then they won't even understand that you haven't had enough resources to actually bring that confidence interval down. So it benefits you as the analyst to really communicate the cost of a good analysis. And that cost can come out with a giant confidence interval. So you know what? We need more resources to run more sims or more replications or gather more data to bring that confidence interval down. So report intervals, don't report points. And that goes along with documentation and reporting. And so this, of course, is also talking about reporting your model. We haven't talked a lot about, documenting these ARENA models. There are ways you can sort of, if you go into the file menu in ARENA and go into their examples, they have some great examples of how you can add blocks of text around the model to sort of help, help give an idea of how the model works and where to go for things. And that's definitely important. It's just, we only have a little bit of time in this class. And so we don't really have the time in the class to go into good model documentation, but I hope you at least understand the importance of it. And then, finally, the final version that's out there. So the thing that you actually run, as well as the thing that you provide into the archive for others to use later. So this is going to be the case regardless of what type of any simulation model you generate in any language, any type of simulation is going to follow through this. So the general method for evaluating a sim is whether it's illuminating and useful. So I hope you get coming out of this that all models are wrong. It is not our goal in sim to build a perfect replication of the real world, because that's impossible. I hope you're seeing that in your final project, is that there are all of these nuances you could put in, but it would take you forever to simulate. And once you got that complicated, then you might not trust any of your model because there'll be all these parameters that you'd have to fit. There is this new thing in simulation now. It's not that new, but it's very trendy now, called digital twins. Twins, like another version of me standing here. And a digital twin is a high fidelity computer simulation that runs in parallel alongside the real system. And it is meant to sort of be a sandbox for you to evaluate changes in real time that you're proposing. In order for digital twins to work, you have to constantly be dumping data from the real system and recalibrating in real time. So you fly this model next to your real system, and because all models are wrong, and these models have got a whole huge number of parameters, there's all sorts of ways for them to be wrong. And the way digital twins get around them being so wrong all the time is this just constantly getting rid of that drift by syncing the data over, because they're right for a small window of time. So they're illuminating and useful for a second or two, and then they have to get a new dump of data and another second or two, because after a second or two, then they stop being that useful. They stop being illuminating and useful. So that's kind of your goal. How do I make the model illuminating and useful? If it's a very high fidelity model, you're going to have to get a whole lot of data, and probably a whole lot of data, maybe even over time, and constantly recalibrating it. If it's a lower fidelity model, then it can actually be useful for longer periods of time and much more generalizable without the data burden. So simple models are sometimes better models, what I'm kind of getting into here. So that's kind of the general message here that we've got coming out of the class here. So I just want to remind again of the timelines. I mean, this week, not a whole lot going on, but keep working on those projects. Next week, we've got the final exam review, resources online. By Wednesday, make sure you've uploaded your project presentations and your reports. Make sure your project presentations don't go over 10 minutes. You're not going to get penalized if they go over 10 minutes, but there's no guarantee somebody's going to watch any longer than 10 minutes. So if you can do a complete and elegant and concise presentation in 8 minutes, that's great. No one ever complained about a short presentation. What people do complain about if a presentation is short is if it's not complete, if it like leaves a lot of questions unanswered. But as long as you present your model and answer all your questions and tell a compelling argument, it's great if it's 8 minutes. I do want to mention one thing, it's kind of a larger point here. I don't know where, but I'm guessing some of you at some point in your engineering career have heard that it's always good to start a presentation with an agenda slide. And some of you might have heard that, or some of you not. At least when I was in your shoes, then that was they said, you always want to start with an agenda slide. Tell them what they're going to hear, and then at the end, it's kind of like what I do with these. This is sometimes I kind of have the kind of agenda slides. Tell them what they're going to know, tell them it, and then tell them what you told them, or something like that. That's fine in general. When you give like a 50-minute presentation, don't do that for a 10-minute presentation. No agenda slides, please. They just waste time. Everybody's agendas are going to be the same. They just distract from the rest of the presentation. And so use that time in better ways rather than rushing up against it. Because I can guarantee you, if for most of your agenda slides, they're going to look identical, and it's going to be somebody saying, well, first we're going to introduce our system, and then we're going to tell you about our model, and then we'll tell you about some of our results. It's just not useful. So I know all that's coming. If it's a 45-minute talk, then I actually might want to know, okay, so I need to see the chapters. I kind of need to know where we're going. But if it's a 10-minute talk, I can already see the end of the talk. I kind of know where it's going already. So I don't need that anchor slide. I don't need that agenda slide. So no agenda slides, no outline slides at the beginning. Save the time for you and for the person watching. They're excruciating. What's nice is that since you upload them, somebody can fast forward through them. So if somebody's if somebody is better off skipping that material anyway, don't put it in. So your project report, 4 pages. Then by Saturday, you're going to do those peer reviews, and then the final exam. So Thursday of next week, stage 1, Thursday of finals week, stage 2, but these are all online. Same setup as the midterm, and the availability window is a little bit larger, just like in the midterm. So you've got plenty of flexibility on when to start these. You can come to class for these, but you don't have to. So any questions about any of that? And then course evaluations, as a reminder, are available. They will be available till December 1st. Questions online? Yeah. Mm-hmm. I have to see what I put on the Canvas availability. So I forget what I set that window at. but it'll be at least the window now. And I could probably be talked into expanding it a little bit as well. That's right. If you'd like to come here and just because you'd say like everybody's got it on their schedule, may as well come here and work on it in class, that's totally fine, just like in the midterm. But if you'd like to do it, and that also will be available all of that Thursday for sure. But again, I think I've made that availability window like because it's at the end of finals week, I don't go very far after, like it might be Thursday and Friday, but I might open it up Wednesday. I just need to see what it's set on Canvas. So whatever is currently on Canvas is the availability window. It's definitely that. And again, I could probably be talked into making it a little earlier, but not later because got to get them in to do the grades. Mm-hmm. Well, yeah, that's you can come here during that scheduled time. That's what I'm saying. If you want that time, I will be here during that time, which is like Thursday at 2:20 or something like that. I think I've got it on the calendar entry on Canvas, but the standard time for this class period, you can come here, I will be here, and you're welcome to work on stage 2 during final exam week. But if you'd rather do it another time, do it elsewhere, that's fine. If nobody shows up, if I'm here and like nobody else is here for 15 minutes, I'll probably leave. But I mean, even if I'm not here, like if you decide you want to come in a half hour later, I mean, nobody else will be in the room. So you can. It is. It is. Yeah. So if you go to the ASU final exam schedule, it says like every Tuesday, Thursday class at 1:30. Is that right? That's right. During the right. And again, if it helps, I think I already put it on the Canvas calendar when the period is for this class. But I can also send out an announcement to say, by the way, this is the final exam period when I will be in the class and the class will be available for people to come and work if you'd like to work. Question online for the final. Yes, there will be a window similar to that of the midterm. So if you go to if you unlock the final exam module and then you click on the stage 1 exam or the stage 2 exam, it should list its availability. And that availability window is longer than 24 hours. So you'll have at least 24 hours, I think at least 48 hours to do stage 1. When you start it, I give you 90 minutes for technical issues to finish it. But for stage 2, it's just going to be open during that whole availability window. And you can go to it and come back to it and so on. So just like the midterm. Any other questions? All right, so the next thing to think about then is just, Tuesday, we'll have the final exam review. Bring your questions. I do have some stock slides. They're kind of, again, the greatest hit slides from the beginning. I'll probably start with the post-midterm ones, and then I've got some kind of ones pre-midterm. They're just meant to kind of be food for thought or fodder for generating questions. If you'd like me to work problems or whatever, I can get out the tablet and work the problems. If you just have questions to answer, bring those. That's the kind of time for that. Or if you don't have none of that and you just want to, sit through the kind of slides I've got available and wait for those questions to come up, that's fine too. So, but if you do have questions, definitely, try to generate them over the Thanksgiving weekend and bring them to Tuesday's class because that's our review. Otherwise, that's all I've got for you. So we'll end a little early today, and this will be your final attendance exercise for the day. So I'll put the link there. The question is in the box right there, over box. So. And if any questions do come up about your final project, or you need sort of ideas or whatever, send me a note. It'll be easier before the Thanksgiving weekend or Thanksgiving break than during, but I will do my best to get back to you as soon as I can. And if I don't talk to you, I hope you all have a nice Thanksgiving break and get a little bit of chance for rest and relaxation. Any questions online? And thanks to the Happy Thanksgiving, you too. If not, I'm going to stop the recording.